Welcome back to the last part of the salts lecture. As I said, I was going to record it after our live online session this morning, and you can see that I'm wearing the same clothes from that session. So that should convince you that I left the video call that we were on and came upstairs and started recording this lecture. Now, if you watched last week's salts lecture, you might be worried as to how much material there is in this week's salts lecture. But the good news is I had a look at the PowerPoint slides and there are only 7 or 8 slides to go, and there's only one key topic left to discuss. So it won't take as long as last week. And if you want to, watch through the video. If there are any things that you don't fully understand, I think we might have another live online session coming up, or you can fire me an email and you can ask me, and I'll do my best to clear up any queries that you have. Right, so with that, the last remaining topic is dissolution of salts. So on the screen in front of you is a classic dissolution equation. It is the Noyes-Whitney equation, which I hope you are familiar with. What it says is the rate of loss of mass of a material, so that's dm by dt as a function of time, so mass with a function of time, is equal to dA upon h st minus c. What are those terms, I hear you ask? So d is a diffusion coefficient, so that's how fast the drug molecule can diffuse through water. A is the surface area of your dissolving solid. H is the thickness of the boundary layer. If you're not quite clear what a boundary layer is, then I shall explain that in just a second. S is the solubility of your compound, which should be a constant, and C is the concentration of that material in solution as the material is dissolving. What does this mean for dissolution in general? D is a constant. A, at least in principle, is a constant. It certainly can be made to be constant, but for our purposes we're going to assume it's constant. H, which is the thickness of the boundary layer, should also be a constant. So what that means is dA upon H should reduce to a constant because every term in it is a constant. Solubility for a given compound is constant, so dissolution should be proportional to concentration. At the start of the experiment, when you put, say, a tablet or something like that into the dissolution bath, the concentration of drug in solution is 0. S minus 0 is S, dm by dt equals dA upon h times S. In other words, the dissolution rate is maximised when the concentration is 0. As the concentration starts to increase as the material dissolves, then the C term starts to get bigger, and then St minus C starts to get smaller. dA upon h is a constant, so dA upon h multiplied by a term which is getting smaller means that the rate is getting smaller. In the limit, the most drug you can dissolve in solution is going to be equal to the solubility, so at that point concentration will be the solubility, so solubility minus solubility is 0, 0 times a constant is 0, and dissolution stops. So what this equation says is that the rate of dissolution is constantly changing. It starts at a maximum when the concentration of drug in solution is 0, and it stops when the concentration of drug in solution reaches the solubility, which kind of makes sense, right? The thing is, what is the boundary layer? Because it's kind of an important term, and it's certainly important for salts. So you've got to think about how material actually dissolves in the first place. So you have a solid, and then molecules are breaking away from the surface of that solid into the bulk solvent. What that means is if you measure the concentration of the solute in solution, you will find that at the surface of the dissolving solid, the concentration is going to be very high. In principle, it's going to be a saturated solution actually. So the concentration around the surface of the dissolving solid is saturated, and as you move further away from the surface of the dissolving solid, the concentration starts to reduce. And when you get far enough away, it will reduce to the lowest concentration and will remain constant, and the material is said to be bulk solvent at that point. Okay, so that region in terms of distance from the surface of the dissolving solid where the concentration is not at its lowest, so it's higher than that of the bulk solvent, is the boundary layer. The boundary layer is really important. Think of yourself as a molecule dissolving from the surface of a solid. You have to break free from the crystalline lattice and dissolve into solution. And you are not seeing bulk solvent. You're seeing a saturated solution of molecules like yourself. So you're really dissolving into a saturated solution of yourself. Now in principle this would not matter for most materials that are dissolving. There's a concentration dependence, but otherwise it doesn't really matter. But I hope you remember from last week's lecture that when a salt dissolves in water, it has the propensity to change the pH, because a basic salt contains a conjugate acid and an acidic salt contains a conjugate base. Okay? And also, I hope you can remember some of those graphs I showed you. The change in pH can be really quite dramatic, at least 3 or 4 pH units, depending on the concentration of the salt that can be achieved. Now that's important for salt dissolution, and it's important because when you dissolve a salt in a dissolution test, you're probably going to use some sort of buffer as your dissolution medium, and so that buffer is going to be, I don't know, pH 3, 4, maybe pH 6.8, whatever it is. When you do a dissolution experiment for salts in a series of different buffered solutions, you would expect the rate of dissolution to be different, because salts are critically dependent on the pH of the medium in which they're dissolving. Okay? But when you do the experiment for real, what you often find is that the dissolution rate of salts appears to be independent of the pH of the buffer. In other words, it doesn't matter which buffer system that you use, you get the same dissolution rate kinetics when you do the experiment, and that can be a little bit confusing. So to understand that, you really need to understand what's going on in this boundary layer. So on the screen in front of you is my rather terrible diagram of a dissolving solid. That's the black circle on the left hand side, and it's showing you the boundary layer in a light grey. That boundary layer is the region of solution where the concentration is higher than the concentration of that salt in the bulk solvent. On the right hand side is a diagram that shows you the pH that the solution actually is as a function of distance from the surface of the dissolving solid. So on the left hand side you are actually at the surface of the dissolving solid. H, which is on the x-axis, is 0, because at that point there is no distance away from the surface. You're at the surface of the dissolving solid. And this is just a theoretical case. Imagine, for instance, that this is a dissolving salt and the pH of the bulk solvent is 7, but because it is a basic salt it contains a conjugate acid, and so as it dissolves it's actually dropping the pH. So this is a calculated graph, and it calculates that because of the concentration of salt that can be attained in a saturated solution, the pH drop is almost 3. So what that means is when the boundary layer is 0, so at the surface of that dissolving solid, if you were to measure the pH at that point, the pH is nearly 3. As you start to move away from the surface of the dissolving solid, the concentration starts to drop, and as a consequence the pH starts to rise. And when you get to the end of the boundary layer, that's the point at which the concentration is equal to that of the bulk solvent, the pH returns to 7, because that's the pH of the medium in which we're dissolving. So you can see, I hope, it's a little bit confusing, so take your time to read through this graph. As you move away, H equals 0 to H equals H, the pH of the medium is increasing because the concentration of the salt is decreasing the further away we go from the surface. And once we get past the boundary layer, we go back to the pH of the bulk solvent. Okay, I hope that kind of makes sense. The important thing here is that you have to remember, if you're a molecule of salt and you want to dissolve into this solution, you are going to dissolve at the point when H equals 0, and the pH at which H equals 0 is nearly 3. So although you do the experiment and you're thinking that you're measuring dissolution in a medium of pH 7, from the molecule's perspective, it's actually dissolving in a medium of pH nearly 3, and that has a fundamental difference on how it behaves. Right, that pH of that boundary layer is quite important then, because it's the actual solution into which your material is dissolving. It's not dissolving into bulk solvent, it's dissolving into the boundary layer, and therefore it has a special name, and it's called pH microenvironment. Now microenvironment is quite a long word, and so it's a lot easier to shorten that to PHM. So as you watch through this video, sometimes I say pH microenvironment, sometimes I say PHM, just depends on how I'm feeling. When I write it, I usually write PHM because it's a lot quicker. It's a little bit unfortunate that every term we're talking about begins with M. So the other key concept was pH max. So pH max and pHM are completely different things. pH max is a point of intersection on the solubility graph of a salt as a function of pH. And pHM is the pH of the boundary layer, at the surface of a dissolving solid. So two different concepts, but they're kind of related, as we'll see in a minute. And in principle, when H equals 0, the pH of pHm should be equal to that of a saturated solution of that salt, remembering that that can drop the pH quite a lot for a basic salt, or increase the pH quite a lot for an acidic salt. Right, this graph simply shows you some data for haloperidol. Funnily enough, it was recorded by Sirajudin again, and I said Sirajudin is a really nice guy, and so this is a really good paper. I think it's quite worth reading through this paper. It really explains some of these concepts of salts, actually. And so what he did was he measured the dissolution rate of haloperidol salt in a series of pH media, 1, 2, 3, 5 and 7 pHs, and essentially he measured the same dissolution rate kinetics in all of those different media. And so he asked himself the question, why? Why am I measuring the same rate in each medium? And so when he calculated, it's quite difficult to measure this for real. You can't really stick a pH probe in the surface, at the surface of a dissolving solid. So you've got to calculate these from the Henderson-Hasselbalch equation. That's right. So he calculated these from the Henderson-Hasselbalch equation. I hope you can see that at the bulk solvent, when you got to bulk solvent, so after the boundary layer, the pH would be 1, 2, 3, 5 and 7, because those are the media that you're dissolving into. But when you calculate what's the pH at the surface of the dissolving solid, remembering that when a salt dissolves, it in this case it lowers the pH, you can see that they've bunched right up, and we've got a spread of pHs between 1 and 3. So even though you think you're doing the measurement between pH 1 and 7, from the perspective of the molecule, you're actually doing the experiment between pH 1 and 3. And then as a consequence, you get relatively similar dissolution kinetics, even though your pH of the medium is quite different. So this is another factor which is going to play into dissolution of these salts in vivo, because again, we talked last week about your GI tract as being a long tube, the pH of which is changing as you progress down it. And it's very simple to think all you've got to do is assume that at one pH the material dissolves, another one it doesn't. But it's not quite as simple as that, because if you've got a solid and it's dissolving slowly, it's creating its own boundary layer, and then the material is dissolving into that boundary layer. Keeping that boundary layer small is the reason why dissolution tests are stirred, actually. So normally you stir at a constant rate, say 100 RPM or 300 RPM, and the reason is to keep the boundary layer as thin as possible. Right, so there are some consequences of this, as shown on the slide. One is that the dissolution rate can be seen to be independent of the pH of the medium, as I just showed you. Another one is that the dissolution rate of your material might change upon storage. Now, I said right at the start of this lecture, the sort of key outcome for you to understand is this interplay between pHm and pH max, and what that means for stability. If you remember from last week's lecture, pH max is really important, because on one side of pH max, your material will either be a salt, and on the other side it will be either a free acid or base. So it's really important what the pH is surrounding your solid, because it will either keep it as the salt or it will convert it back to the free acid or base. And I said that's something to worry about in vivo. But it's also a problem on storage. Storage is a very important theme for pharmaceuticals, obviously. So on the screen in front of you there is an example paper that I really think you should read. It's by Zanu, it's in IJP, so not too difficult to find and download. And so the paper reports a study of a formulation of a malleate salt. Okay, that malleate salt was formulated as a tablet and as a capsule. Two formulations were put onto accelerated stability trials. That's higher temperature and elevated RH, so they're exposed to some water. And what happened is, after the storage period, the tablet formulation of that salt, it says it lost potency, but it effectively the drug disappeared, but also the dissolution kinetics changed, and the capsule formulation did not. So the capsule was stable upon storage, and the tablet was not. So the question is, what happened to this formulation that meant that the tablet was unstable on storage and the capsule wasn't? And the answer is, it's quite a clever thing that happened. It's the chemistry of salts at play. The tablet was just directly exposed to the humidity. So what that meant is the humidity was quite high, 75% relative humidity, so you get quite a bit of water condensing on the surface of the tablet. So water condensing on the surface of a tablet is not really any different from a boundary layer surrounding that tablet in a beaker of buffer as you're doing a dissolution test. So you get water condensing on the surface of that tablet, and then some of the material which is in the tablet can dissolve into that water layer. Because it's going to dissolve to quite a high concentration, it's going to be a saturated concentration in that water layer on the surface of the tablet, and therefore it can have quite an appreciable change in pH from just plain water, because it's a salt which is dissolving. So in this instance, the pHm, so that's the pH microenvironment, so that's the pH which the salt dissolving into the water on the surface has created, was 4.3, but the pH max was somewhere between 3.3 and 3.6, so the pHm was higher than the pH max. And the consequence of that was that although there was a salt in the tablet formulation, within that boundary layer, a conversion back to free base occurred. And in this particular instance, the free base happened to be volatile, so it would sublime. And so it actually sublimed off. And so can you imagine what happens? You have drug as a salt in the tablet. You have water condensing on that tablet. Some of the salt dissolves in that water layer. The pH increases, it goes above the pH max, the salt converts to the free base, and in this particular instance the free base was volatile, and so it volatilized, which means more drug can then dissolve from the tablet and the process can just repeat. So on storage you got this gradual but continuous volatilization of the salt, and so by the time the tablet was taken off the storage trial, there was actually no drug left in the tablet because it had volatilized and gone. Quite an interesting example, I think, and I highly recommend looking to see what in that paper to see what that was all about. I highly recommend it because quite often in the exam that accompanies this module, I ask a question about the storage of salts in formulations with respect to water. And so when I'm asking that sort of question, what I'm looking for is this interplay between pH max and pHm and what it means for the stability of the compound. Okay, now have in the past had an instance where I asked a question like this in an exam and some students said, okay, I think what must have happened is that in the tablet the material was amorphous and that's why it dissolved fast, and when it got wet under storage it crystallized and that's why it didn't dissolve very well after storage. Which is a completely reasonable answer. If the material was amorphous in the first place, that's a really reasonable explanation of what might have happened. But in this particular instance, if the question is asking about a salt, then really the answer is going to be involving salt chemistry. So if you see that the question is about salts and it asks you something about what might have happened to this tablet on storage with respect to water, I don't want an answer about amorphous materials. I want an answer about salt chemistry and this interplay between pHm and pH max. Okay, it's really important that. Now, if you're following what I'm saying, which is that tablet contained salt, and that salt was dissolving into this water layer, and then because the pH M was above the pH max, it was converting to the free base, and that was causing a problem. You might say to me, two things actually. One, why was the capsule okay when the tablet wasn't? And the answer is, and that's a good question, the answer is that the capsule has an outer shell and your material is inside it. And so although it was exposed to the same humidity conditions, that water wasn't actually getting to the salt itself. And so that conversion couldn't happen because the salt never actually got wet. You could do the same thing to protect the tablet, for instance, by film coating, couldn't you? So film coating the tablet would protect it. So that's one thing. Another thing you might say, if you're really switched on to this idea, and I think this is a really key and clever way of thinking, you might say to me, oh, hold on a minute, tablets are not containing just drug. They always have excipients in as well. Even if they're just bulking out, they have excipients. And those excipients also have the capacity to dissolve into that surface layer of water. So you could say to me, why don't we add an excipient into that tablet which is going to dissolve into that water layer as well, and try and keep the pHm below the pH max? So without doing anything, in this particular instance, the salt was dissolving into that boundary layer and the pHm was rising above the pH max. wouldn't it be a good idea to add an excipient that could dissolve and stop that pH change? And that's exactly what they did. Now, you might say to me, okay, well, there's loads of excipients I can add into tablets. Surely only very few of them change the pH of a microenvironment, but actually you'd be surprised. So this table shows you some really common excipients that you might use in a tablet formulation, and it shows you the pHm that they will create in a saturated solution. So if I pick some examples, PVP, polyvinyl prolidine, if that dissolves to saturation, then it will in water, then it will create a pHm of 3.7. I'm quite surprised by that. So that's lower than I thought. MCC somewhere between 4 and 4.7. Lactose 4.2. If I just go down to some more alkaline examples, maize starch 6.3, calcium carbonate potentially up to 8, and so on. So actually, most of the common excipients that you might include in a tablet have the potential to change the pHm when they dissolve. And that will occur in the dissolution experiments as well as this stability thing that we're currently talking about. So if you go back to that Zanu paper, and I still think it's highly worth reading it, they realised that this is a potential formulation strategy. And so what they did was they added an excipient in order to lower the pHm. And obviously, if you want to lower the pHm, the best thing to add is an acid. So in this instance, they added citric acid to their tablet. So what that meant was on storage, some of the salt was dissolving in that water layer, but citric acid was also dissolving in that water layer. And because it's an acid, it naturally brought the pH down again. And so what they did was they managed to reduce the pH of that microenvironment at the surface of that tablet to below 3. So then it became below the pH max, and as a consequence, although the salt dissolved into that layer, it didn't then convert back to the free base, and so it didn't volatilize. So it's a really clever thing to think about. It's one of those things where you make a tablet, you put it under storage conditions, you recognise it's probably getting a bit wet, but you don't think in your mind, oh, this is what's happening. You just think there's a bit of water. I know that my drug doesn't react via hydrolysis, and so therefore it should be fine. And you can't understand where the drug's gone at the end. And it's just one of those things where I suppose it's important just to think about salt chemistry. Whenever you're dealing with salts, think about salt chemistry. Because even though there's not a lot of water on the surface of a tablet, in this particular instance, because the free base was volatile, it meant that that surface was acting like a catalyst. And so over a long period of time, that conversion happened almost to completion and the drug disappeared. Last thing to think about, and then we're good for a summary, is that I've alluded to this a number of times as well. You've got to think about salts as ions. When they dissociate, they're ionised, and I've said a number of times, ions do not cross cell membranes. And so if you get your salt chemistry right, you can make it so that in the small intestine or the large intestine, you actually have the predominance of the salt form. And if you do that, you actually hinder absorption across the gut wall, because ions don't go into the membrane. If you're trying to deliver the drug systemically, that's not great. And it's one of the reasons why acidic salts, for instance, can be a bit tricky to be delivered orally. But those clever people that are thinking about treating gut conditions, so you're trying to get drug acting locally in the gut, realise that actually that can be a formulation strategy. By making the drug ionised in the gut, you are actually preventing it being absorbed. And if you want it to act locally, that's actually a way of increasing the concentration in the gut to get some sort of local effect. And so I simply note here that prednisolone and sulfasalazine are both examples of drugs that have been formulated as salts precisely to try and target their action in the gut. And who knows, maybe some of you will have picked those drugs as examples for your coursework. There's still time, just once you watch this lecture, if you want to change to that. Yeah. Right, so what that means is we're at the end, which I'm sure you're glad to hear. To be honest, I was surprised last week that once I'd finished recording the first parts of the salts lecture, I think in total we were almost at 2 hours worth of video, which in real time in the lesson would have been nearer 3 hours. I was quite surprised by that. So that means this lecture has been a lot shorter, and I'm sure you're pleased about that. On the screen is a summary of what I think you need to remember about salts. It's a really key topic, and when you're doing revision for the exam, without telling you what's coming up in the exam, I suggest focusing on salt chemistry. Okay? So remember, salts are a strategy to improve all sorts of things, not just solubility, but in the main it's solubility. But salt formation can improve a number of other physicochemical properties of your drug. But because they do that, and also because they impact bioavailability, you have to make a decision on salt former really early in the development process. Solubility increase is often achieved at the expense of permeability. So when something goes into water, it's ionized, that improves water solubility, but then it won't cross a cell membrane because it's ionized. So that's a bit tricky. That actually means that a basic salt has the best kind of chemistry for oral drug delivery, and an acidic salt doesn't. Salts form when an acid reacts with a base. You should know that. You've got to choose a really sensible salt former, preferably with a pKa difference of at least 2, ideally 3 or higher. Really key, a basic salt contains a conjugate acid. Acidic salt contains a conjugate base. Therefore, when you dissolve those salts, the pH either drops or rises depending on what you're dissolving. So it's kind of important to recognise. Basic salt contains a conjugate acid. So when you dissolve it, you recover your free base and you drop the pH, and vice versa for an acidic salt. Salts themselves has the same solubility as the free acid or base. The reason is because what you end up with in solution is the free acid or base, so therefore the solubility is the same. It's the same thing that's dissolved, right? The only difference is that because of the conjugate acid or base, you've changed the pH. Therefore, if you try and dissolve into a buffer, you won't change the pH, and then you don't change the ultimate solubility. You might at this point say to me, didn't you just say that when you do dissolution testing in different pH media, you get the same dissolution rates? So the concept of the same solubility in different buffers is because it's a bulk thing, and the different dissolution rates in pH media is because of the pH of the microenvironment. So pH microenvironment is really important for controlling dissolution kinetics. pH max is really important for controlling stability, and pH max and pH M interact with each other to control the stability of your salt when they're in water. Right, with that, if you have any questions, fire me an email or talk to me in the next online session. Otherwise, I'll see you soon.